Why does salt dissolve in water, but oil doesn't? Well, in a word, chemistry. But that's not very satisfying, is it? Well, the reason salt dissolves and oil does not comes down to the two big reasons why anything happens at all: energetics and entropy. Energetics deals primarily with the attractive forces between things. When we look at oil, or salt in water, we focus on the forces between particles on a very, very, very small scale, the molecular level. To give you a sense of this scale, in one glass of water, there are more molecules than known stars in the universe. Now, all of these molecules are in constant motion, moving, vibrating, and rotating. What prevents almost all of those molecules from just flying out of the glass are the attractive interactions between molecules. The strength of the interactions between water itself and other substances is what we mean when we say energetics. You can think of the water molecules engaging in a constant dance, sort of like a square dance, where they constantly and randomly exchange partners. Put simply, the ability for substances to interact with water, balanced with how they disrupt how water interacts with itself, plays an important role in explaining why certain things mix well into water and others don't. Entropy basically describes the way things and energy can be arranged based on random motion. For example, think of the air in a room. Imagine all the different possible arrangements in space for the trillions of particles that make up the air. Some of those arrangements might have all the oxygen molecules over here and all the nitrogen molecules over there, separated. But far more of the possible arrangements have those molecules mixed up with one another. So entropy favors mixing. Energetics deals with attractive forces, and so if attractive forces are present, the probability of some arrangements can be enhanced, the ones where things are attracted to each other. So it is always the balance of these two things that determines what happens. On the molecular level, water is comprised of water molecules, made up of two hydrogen atoms and an oxygen atom. As liquid water, these molecules are engaged in a constant and random square dance that is called the hydrogen bonding network. Entropy favors keeping the square dance going at all times. There are always more ways that all the water molecules can arrange in the square dance, as compared to if the water molecules did a line dance. So the square dance constantly goes on. So what happens when you put salt in the water? Well, on the molecular level, salt is actually made up of two different ions, chlorine and sodium, that are organized like a brick wall. They show up to the dance as a big group in formation and sit on the side at first, shy and a bit reluctant to break apart into individual ions to join the dance. But secretly, those shy dancers just want someone to ask them to join. So when a water randomly bumps into one of them and pulls them into the dance away from their group, they go. And once they go into the dance, they don't come back out. And in fact, the addition of the salt ions adds more possible dance positions in the square dance, so it is favored for them to stay dancing with water. Now let's take oil. With oil, the molecules are sort of interested in dancing with water, so entropy favors them joining the dance. The problem is that oil molecules are wearing gigantic ball gowns, and they're way bigger than water molecules. So when an oil molecule gets pulled in, their size is really disruptive to the dance and the random exchange of partners that the waters engage in, a very important part of the dance. In addition, they are not great dancers. The water molecules try to engage the oil molecules in the dance, but they just keep bumping into their dresses and taking up all the room on the dance floor. There are way more ways the waters can dance when the oil gets off the floor, so the waters squeeze out the oil, pushing it back to the bench with the others. Pretty soon, when a large number of oils have been squeezed over to the side, they band together to commiserate about how unfair the waters are being, and stick together as a group. So it is this combination of the interactions between molecules and the configurations available to them when they're moving randomly that dictates whether they mix. In other words, water and oil don't mix because they just don't make great dance partners.